Now we're looking at repeated eigenvalues. So when a system has repeated roots, the lambda 1 equals lambda 2, we're said to have eigenvalue of multiplicity of 2. So our first solution is just C1 K1 e to the lambda 1 t, just the same as before. Our second solution, x2, is going to be C2, and then we're going to repeat this root except it's being multiplied by t, so it's going to be K1 t e to the lambda 1 t plus p e to the lambda 1 t. K1 and p are vectors. And K1 we found just the same as before. P is found by a minus lambda I times p equals k. So we know from before we found k by a minus lambda I times k is equal to 0. So we're going to have to find this first, and then when we go to solve for p, then we have the a minus lambda I times p is equal to k. So we'll already know what that k is. So our method is 1, find the lambdas, those eigenvalues. And in this case, lambda 1 is going to equal lambda 2. We're going to find that determinant. Equals 0. So that's how we're going to get k. So find associated k vector. And again, we found that by a minus lambda I times k is equal to 0. So again, it's exactly what we did in the other. And then we have to find vector p. And we're going to take that a minus lambda I, multiply it by p, and set it equal to k so we can find vector p. So our general solution, C1 K1 e to the lambda t plus C2 K1 t e to the lambda 1 t plus p e to the lambda 1 t. And that C2 is distributed over all of that. If we have multiplicity 3, so we had a triple root, lambda 1 equals lambda 2 equals lambda 3, then our C1 is just going to be, our X1 is going to be C1 K1 e to the lambda 1 t. Our X2, C2 times K1 t e to the lambda 1 t plus p e to the lambda t. And our third is going to be C3 k t squared over 2. We're getting factorials out of here. e to the lambda t plus pt e to the lambda t plus q e to the lambda t. And q is found by a minus lambda I times q is equal to p. And it would just keep going on if you had more and more roots. And again, you're going to wind up with factorials. So for our first example, we have x prime is negative 6, 4, 0, negative 6 times x. So first I want to find my lambdas. So take the determinant, and again, it's lambda I, so it's the identity matrix by lambda, so you just get lambdas on the diagonal. So I get negative 6 minus lambda, 4, 0, negative 6 minus lambda. So finding that determinant, we do the cross products. I get negative 6 minus lambda times negative 6 minus lambda minus 0 times 4, which is just 0, equals 0. So here I have a double root. And I get lambda is equal to a negative 6. And that's lambda 1 and lambda 2. They're both the same. Next, I need to find k. So when I go to find k, I have my a minus lambda I. So here's a. So I'm going to take on the entries and subtract lambda, which was negative 6. So negative 6 minus a negative 6, I get 0, 4, 0, and then again here, I get a 0. And then k1, k2 equals 0, 0. So the first one, I do this matrix multiplication. I get 0 times k1 plus 4 times k2. So 0k1 plus 4k2 is equal to 0. And then for the second one, I get 0k1 plus 0k2 equals 0. So this 0 equals 0, I have infinite solutions. For this first one, k1 could be anything. I'm going to let 4k2 is equal to 0, so k2 is equal to 0. So k1 can be anything, and k2 equal to 0. So because it can be anything, we usually pick something really nice like 1. So k1 is just going to be 1, 0. Now I have to find p. And a minus lambda I times p is equal to k. So a was negative 6, 4, 0, negative 6, minus lambda I, and lambda was negative 6, so negative 6, 0, 0, negative 6. And then I'm going to have to multiply that by p1, p2, and it's going to equal k, and k was 1, 0. So negative 6 minus a negative 6 gives me 0. 4 minus 0 is 4. 0 minus 0, and negative 6 minus a negative 6. And it equals 1, 0. So do our matrix multiplication. I get 0 times p1 plus 4 times p2 is equal to 1. And I get all zeros for the second one. So 4p2 is equal to 1. p2 is equal to 1/4. p1 could be anything, because I have that row of all zeros, so we know it's an infinite solution. So I'm going to let p1 equal 0 and p2 equal to 1/4. Just to make it simple, you don't have to pick 0, but makes it simple. So p is equal to 0, 1/4. Or you can pull out the 1/4, which happens a lot, just because they like these vectors to be nice, simple whole numbers. So our general solution is xt equals C1, k was 1, 0, e to the negative 6t, plus C2, and then we repeat that, it's just there's a t with it as well, so we get 1, 0, t e to the negative 6t, plus 1/4, and then p was a 1401 e to the negative 6t.